Counting techniques are different ways to come up with large numbers without having to look at a situation and physically add up 1 plus 1 plus 1 plus 1 to see how many different ways an experiment can be done. So we're going to talk about the die, and it is a commonly used example for probability. Now, first of all, let's define some terms. Outcomes are the different possibilities when you roll the die. So in this case, my outcomes would be 1, 2, 3, 4, 5, and 6. So it's just listing the possibilities that can occur when you actually do the experiment. The sample space is actually just like the outcomes. It's all the different possibilities. So 1, 2, 3, 4, 5, and 6. Now, you may be wondering, well, why do we have two different words for the same thing? The sample space are all the different ones. The outcome is specific to whatever the question's asking. So if I'm asking, what is the probability of rolling a 1? So the outcome that I'm specifically looking at is 1. So there's one way I can roll a 1 out of the sample space, which is 6. So the outcome is specific to the event that the problem is asking. The experiment would be just rolling the die in this case, because you're doing an experiment to find out what the probability is of rolling a 1. And the probability is the number of ways you can receive the outcome over the total sample space.
So I was thinking how...
So the number of ways we can have an outcome, so there's only one possible way that we can roll a 6 out of the total number of outcomes or the total sample space, which is the 6. So the probability of rolling a 1 is 1/6. These are some other types of questions that you're going to be getting. There are 6 meat choices, 3 cheese, and 11 veggies to make a pizza. How many different pizzas can we make with 1 meat, 1 cheese, oh, I forgot the E there, and 1 veggie? This is called the fundamental counting principle because all we have to do is take how many choices we have for each. So we have 6 meats. We have 3 cheese, and we have 11 veggies, and we're simply just multiplying them together. That will give us our total number of outcomes, meaning the total number of different pizzas that we can make if we are choosing one of each topping. This is the fundamental counting principle, which you can see right there. Okay, so if we're just given a list of items and we need to find out what the total number of outcomes are, we're simply just multiplying them all together. A factorial is a mathematical term for taking a number, so let's say 7. If I say 7 factorial, it looks like an exclamation point. That is equivalent to 7 times 6 times 5 times 4 times 3 times 2 times 1. So instead of writing it out, we can just say 7 factorial because that indicates and implies that we are going to take the first number as the number we see in the factorial and we're multiplying it by 1 less each time. Now, that doesn't seem too hard to go to the calculator and 7 times 6 times 5 times 4 times 3 times 2 times 1. Not a big deal, we can do that. But what if I said 33 factorial. Well, that's equivalent to 33 times 32 times 31, and so on, all the way down to 1. Well, that's going to take a little bit longer. Or let's say I said 100 factorial. That's the same as 100 times 99 times 98 times, and so on. So we can find this on our calculator. Rather than doing it by hand, I'm going to press 7. Then I'm going to press math. I'm going to go over to probability. And then my factorial is number 4. And then press enter. So if I were to multiply by 7 times 6 times 5 times 4 times 3 times 2 times 1, I get 5,040. Now, why do we need to know this? There's different types of problems that we're going to get, and again, we're trying to look at the different number of possible outcomes, but depending on the situation that we're given, we may be able to use factorials in order to get our answer. So in this question, there are 6 textbooks that need to be placed on a shelf. How many different ways can the textbooks be arranged? Well, so I have 6 placements, and I always like to make a visual for this. This is my shelf, and I have 6 spots. Now, when I'm about to place my very first textbook down, I have a pile of textbooks over here, and I'm going to place one of them in my first spot. Doesn't matter which one, so let's say this one. I'm going to put a 6 there because I had 6 to choose from when I put it in the first position. Now I only have 5 left to choose from because that first book is locked into the first position on the shelf. Now I have 4 to choose from because the first 2 books are already placed. And so on and so forth. Now, the reason that I introduced the factorial is because what we've done is we've created a factorial. So we go to our calculator, press 6, math, four, we get 720. Now, this question is also an example of a permutation. And a permutation means that we're finding the number of outcomes and the order of those outcomes matter. And what I mean by order matters is that we cannot take a book and put it in the first spot and then reuse that book in another spot. The order in which these books are placed, they matter, okay? Because the first book is in spot number 1. The second book is in spot number 2. The third book is in spot number 3. Fourth book is in spot number 4. Fifth book is in spot number 5. And sixth book is in the last one. So there's an order to which they have to be placed on the shelf. Now look at the next one. There is 6 textbooks that need to be placed on the shelf, but there's only room for 4. How many different ways can the books be arranged? So here's my 4 placements. Here are my 6 books. I'm going to pick my first book. There's 6 to choose from. Now there's 5 to choose from. Now there's 4 to choose from. And now there's 3 to choose from. I still have 2 books remaining, but I am only picking 4 of the 6. So this kind of looks like a factorial, but unfortunately it doesn't go all the way to the bottom. Now, because the order in which the books matter when they're placed on the shelf, then I'm going to say that this is a permutation. And how I solve this is I say we have a total number of 6 books. It's a permutation, and we're choosing 4 of them. So I'm going to go to my calculator. This is how I do a permutation on my calculator. I hit the total number of items, which is 6, math, go over to probability. The second one is NPR. That's the one I'm going to choose. That means it's a permutation. I'm choosing 4 of them. So there's 360 ways that 4 books can be placed in an order on a shelf. So for permutations, it looks like this. The N is the total number of items. The R is the number that we're choosing. In our last example, it's going to appear very similar to the previous example. So this is where some people may get mixed up a little bit. So pay close attention. There are 10 people in a group. 3 will be picked to go into a hot air balloon. How many ways can 3 people go into the hot air balloon? So here we have 3 people. Yes, they have legs. And here we have the balloon. Now the difference between this question and the question before is the placement of the people in the balloon does not matter. Whereas on a shelf, the books had to go in an order. So with this question, order does not matter, and this is therefore called a combination. Order doesn't matter. So we have 3 people, and we're going to do C3. I'm going to go to my calculator, 3, math, because we have a total number of 3 people, and we're choosing all 3 of them. Now, some of you may be wondering how this is equivalent to 1. How can there only be 1 outcome when there's 3 people and we're choosing all 3 of them? Well, this is why. Let's say I do put an order on these people just for the sake of showing you this example. So we have, and then when they go into the balloon, they could be in the order when they're picked to go in, 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 2, 1, and 3, 1, 2. What we're saying is that the order of these numbers doesn't make a difference. So really, they're just one possible outcome. All 3 of them are being chosen to go into the air balloon. It doesn't matter what position they're standing in because they're all just sitting in the balloon enjoying the scenery. Now, what would make this a permutation is if I said that the first person who went in had to stand on the left-hand side, the second person who went in had to stand in the middle, and the third person who went in had to stand on the right-hand side. Then that would be a permutation. And in that case, we would have 3p3. And if we go to the calculator, 3 you will see that there's 6 different outcomes. Well, let's count. 1, 2, 3, 4, 5, 6. That's exactly what we got. Now, let me say this again. When order does not matter, even though we can rearrange the numbers, they're all just the same outcome. So that's why 3C3 is equal to 1. But if the order does matter, which makes it a permutation, then the position in which they're standing in the balloon makes a difference. So now, instead of the 1 outcome, we have 6 outcomes. That's the difference between combinations and permutations. So here, there are 10 people in the group. 3 will be picked to go in the hot air balloon, 1 at a time. How many ways can the 3 people be picked? So now I'm saying 1 at a time. Okay, that's the same as saying the left, the center, and the right, which is my 3p3, which is equivalent to 6.